about basically what are factorization algebras, some examples, some basic properties. And before I start, I want to start with a bit of a disclaimer, which is that if you read the literature of factorization algebras, there are a lot of different, often slightly different, subtly different approaches where the same word is often used for things which are maybe slightly different or maybe almost the same, but not quite. So just to say that one has to be very careful when reading the factorization algebra literature. And specifically in this lecture series, so this lecture series is based on a paper that I wrote together with co-authors Tashi Walde and her PhD student Irene Carson. But of course, so we of course proved some original things, but also we took a lot of input from many different sources. And throughout this course, so I will just mention a few names now in the beginning, and I will not always be super careful about where everything comes from. We have precise references in our papers for this, but since it's a bit of like it's often a little bit complicated to trace the exact, I will just be very vague about this. So, like factorization algebras, they were defined by many different authors in slightly different ways. So, for example, we have Costello William, we have Rode, we have Mariella, Francis, sometimes with Tanaka, and there's also version of Lurie. And all of these were very heavy influences on our paper, of course. And so one way to say this is that so there are a lot of different papers, all with slightly different conventions. And if there's one thing that is better than having 10 different papers with slightly different conventions, is having 10 plus 1 papers, which was the reason we wrote one more. Yes, so with that out of the way, let me start with some conventions for this talk. So let's see if I can do this right. So I have to switch to this board. Yes. So throughout this talk, whenever I use letters like X, Y, Z, these will always be topological Hausdorff spaces, or Hausdorff spaces. And often, in fact, later on, they will be some sort of manifolds. Maybe with some stratification. But I will say more when that comes up. And then, moreover, I will fix C. This will be some symmetric monoidal infinity category with columns and such that tensor distributes over them. And yeah, this will be fixed throughout the talk. This will just be the target. And of course, there are many different targets that are interested in the literature. Well, for example, some derived categories of some rings, or sometimes even the spaces, sometimes categories, and so on and so on. But for this talk, this will be just some abstract target pattern. Okay, so let me start with the motivating example, at least for me. This is also another aspect, is that factorization algebras are a very flexible thing, and different people have different motivations for studying them. So this is maybe just one perspective, and if you ask other people, they will tell you different reasons or different motivating examples. So let's start with the following. So let's say you have some topological T. I will specifically not use that letter X because this plays a bit of a different role, as we will see in a moment. So let's say I have a pointed space. So like here we need topological space, not anima or this group, but it's really an old-fashioned topological space. Then we all know that the loops on X has some sort of coherent associative structure. And here's one way to make this idea precise. Of course, again, there are many different ways, but let me present one which will lead to the topic of this talk. So one way to make this precise is to observe that one has a functor that goes from the opens of R. And so this R, this will take the role of what later will be my x's, which is why I didn't want to use the same letter here. So there's a functor from opens of R to topological spaces, which let's say call it F, which sends some open to just the topological space of maps in T, which are compactly supported, so that the support of F is compact and also contained within U. And if you now observe what this functor does for you, you will see that maybe now or can really post-compose with to homotopy types, but yeah, a priori this really goes to spaces. If you now observe that whenever you have an open interval in R, if you look at what the value on this open is, this will embed into the space of paths. So these are maps of pairs. So the space of the loops of T. And in fact, this inclusion is easily seen to be a homotopy equivalence. Like if you see what it means to have a compactly supported function that has a compact support on AB, then it's basically, except for the fact that at the outside it's going to be constant for a little while longer, it's basically the data of a path. And so this, of course, is just a homotopy equivalent to the loop space of T. But this was true for every possible interval. And so from the data of this functor F, we in fact see a lot of the coherent structure of this omega x. So from this, we can encode concatenation of paths, because what we can just look at is we can say, okay, we have a real line, and then if you look at nested intervals, let's say we have an interval V, and inside it we have two intervals U1 and U2, then if we look what our functor does to this, we see that we have f of u disjunct union U2, which having a function that's compactly supported on this disjunct union is the same data as just giving the value of the function here and here. So this is just the product of these two. And then, but then since this is really a functor where here this I view as a poset, just by inclusion, and if this is obviously factorial, because if something has support on something smaller, then in particular it has support on something bigger. And so I have a map from here, which is just inclusion really, to f of v. And after we identify this and this, all of them with the loop space, we see that this encodes one version of saying what the composition of paths is. But then it also encodes associativity. So the way I said it now, this after identifying with all these homotopy equivalences, we really get a map like this, at least after homotopy. But then we also have something like associativity. And that just comes from the fact that I can just look at three intervals sitting inside one common interval V. And then if I have f of U1, f of U2, f of u3, then I have two ways of going f of b. I can either choose some interval that's bigger than these two, let's call it u1, 2, or, okay, maybe I'll draw it down here to not clutter the picture too much. I can have something like O, U2, 3, and then there will be a strictly commutative diagonal here a priori, but then once you identify via all these homotopy equivalences, it will become a diagonal that only commutes up with homotopy. So here we will have f of u1, 2. This commutes, and therefore what becomes associativity up to homotopy. And of course, one can keep going and extract as many coherences as one ever wants from this one founder. Okay, so this is like the prototypical example of what is called a factorization algebra. And today I will explain some of the basic properties, like what did we just see here, and what we will do. Let me give first one more example. So that's, I should switch. Thank you. So one can also extend this example to the following. So if I have, let's say I have not just a single topological space, but I have a pointed pair. So S is a subspace. Is a pointed subspace of T. Then I can write down something very similar to this, but now it's something that doesn't go from the opens of R. This doesn't go from the opens of R, but goes from the opens of the half open interval, or like from the opens of the array to top. Call this f prime. And it's the same as before. Let's switch words. So again, we wanted the support of f is contained in U and is compact. But additionally, we have the extra constraint that f of 0, so 0 is somehow a special point here. We want that this really lies in S. That's where the S comes in. And now, if you look at what sort of intervals there exists, so if I have on the half open real line, so I have my positive, like non-negatively aligned. And now, so here every interval had the same value of these homotopy. We will come to this in a moment. The next lecture is will be a very important property. But here something a bit different happens, where if you have some interval here in somewhere away from this point, then once you're away from this 0 point, the S no longer plays any role. So we already saw that up to homotopy, here we really get the loop space of T. But if you look at an open that contains this starting point, let's call it O, then now if you look at what it is, it will be paths that start somewhere in S and then end up somewhere in and end up at the base point in T, but they're allowed to move through T. And if you notice, so if you look closely, then this is just the homotopy fiber of the inclusion of S to T. And in fact, now from this picture, you see a generalization of the fact that here you have a multiplication map, which is that here, if you now take some even bigger interval, if, for example, the whole like this whole interval, it again contains the cone point, so it will be sent to something that's again equivalent to this fiber. And then the inclusion of this union this into this will give you a map like this, which is some sort of action. And this, in fact, is the canonical action of this group onto this pointed set. So this is an action of this on this fiber. And again, similarly to how here you see the associativity, here you can also see the action rules from this picture. Okay, So these two pictures, I hope you will keep in mind because we will see them a few times, and they're somehow the prototypical examples of what will be to come now. So let me start with the actual definition of the main objects we're going to study in this lecture. Okay, so definitions. So we're going to do something a little bit more general. So we're going to allow ourselves the flexibility to have U, and I hope I will be careful with this. So this is a curl U, which you can distinguish because it has a long initial thing, and I will try to make straight U's visually very different by not putting the thing in the middle. So I hope you will be able to see this difference on the board. So let curl U in open of X be some full pole set. So later we will need some restrictions on this, but for now this can be very general. And the first thing we're going to do is we're going to construct an operad out of this, which I will denote. I will just put this tensor symbol to distinguish the operad from the pole set itself. And so this operad, it looks like it follows. So it has, and this is really a discrete operad, not infinity. And it's very explicit. So it has colors are the elements of U. With colored opera, the colors are just certain open subsets of X. And then the sets of operations are very simple, where if I have a bunch of opens and then one more open U, then the set of operations from here to here, there's only two possibilities. Either we have that U1 UN, they all sit inside U, and this dot on the union symbol, this is making the additional claim that the UE are pairwise disjoint. So they're all contained in U and they're pairwise disjoint. If this is the case, then we have a single operation from these to this, and otherwise we have no operations. And with this definition, there's really only one way to turn this into an operad. So this has with the only possible operad structure, like composition and sigma n structure. Yeah, sigma n. Okay, and just to give you some very simple example, just to connect it to something Rune showed you, if you take U to just be the empty set, so like the set it contains a single open of X in the empty set, and if you do this, you will see that this will always be tautologically satisfied because a bunch of copies of the empty set are always disjoint and they're always contained in the empty set. So if you do this, you really just get the commutative operad. Okay. And now we can come to the main definition of this course using this operad. Okay. Okay, I will just erase this little thing. Okay, so here's the main here. So a pre-factorization algebra with values in C And this part I will usually not mention explicitly because our C is going to be always fixed. So I won't really mention where our factorization algebras take place. It's always just going to be our fixed C. But importantly, a factorization algebra on U, so where U is some subposet of the opens of X, is just an algebra, is a algebra for this algebra in our target. And again, when I say algebra, it will always be in our target. So this will probably be the last time I will really explicitly write this, unless there is something very specific. And so such an algebra, if I have such an algebra in C, so also here I will drop the C from the notation when appropriate, is called, so if I have such a prefactorization algebra, it's called a factorization algebra. If additionally the following two conditions hold. If the following. So the first condition is what's called multiplicativity. Which says that whenever I have pairwise disjoint elements in my set of opens, then the map, the following map. So I have f of u1. I have the tangent product of all of these ui's, and the fact that sorry, this was the algebra was called A. So the fact that this is an algebra means that whenever I have an operation in my operad, I will get a structure map, I will get a map in the target category, and I do have an operation where here I just put the disjoint union of all these UX. Because in this case, I will have, I probably would not see it. I have U1 and N, and here I have the union of all of them, and so this will even be an equality. In particular, we'll have an operation, and I want that then the map induced by that operation is an equivalence.
Do you assume that the disjoint union is again in your family U?
I do not, no. So I guess you're right, I should probably, the way I wrote it here, I should probably write such that if the disjoint union exists, then this, if this map doesn't exist, then there's no condition. Yeah, good question, thank you. Yeah. And if you want to do this precisely within Lurie's model of operad, so like the left-hand side, of course, is just a discrete operad, but I mean the target could be some symmetric monodic infinity category. So we should be slightly precise about what this means. So if you think of it in Lurie's style definition, you will have a map over thin star like this. This is what an algebra really is. And what this really says is that the multiplicativity says that this A, it preserves all co-Cartesian edges, I guess P, Q, perfect. It sends P co-Cartesian arrows to Q co-Cartesian arrows. Say it again?
It's strongly monoidal.
It is strongly monoidal, except that this is not a monoidal category. So there might, so not all p-co-Cartesian lifts exist here, but the ones that do need to be preserved. Exactly. So the ones that exist.
Also, I think that maybe this is only an equivalent condition if all disjoint unions exist. Because otherwise you could have like a next bigger set that contains the disjoint union but is universal.
Oh, yes, you're right. I think that might be yeah, there might be a next. Yes, you're right. I think, yeah, this is only yes, this is a good point. Okay, yes. Okay, this characterization is only true if U is closed under disjoint unions. Yeah. Yeah, this will be mostly the case we care about, but yeah, thank you for, yeah, that's true. And so of course, in general, a map of opera only preserves the inert ones, and here we ask for all of them, not only. Okay. But yeah, this is really the way I want to phrase the condition. Then one can rephrase it in this other language. Okay, and then there's a second condition about factorization algebras, which no longer fits in this board. So let me move to this board. So the second condition is so-called Weiss descent. And I will first state it, and then I will spend a little bit of time explaining what this is and why it is useful, or why one chooses this condition. So the underlying functor. So of course, this operad U tensor, it contains U as its underlying category of one-area operations. And so my factorization algebra A will induce, if I just restrict to the one-area operations, it will just induce a map from U to C. And the second condition I'm writing is only a condition about this functor. So this is no longer anything about operads. This is just saying that this functor satisfies Weiss descent. And I will explain this in just a moment. I will first finish the definition, and then I will spend some time explaining what this means. And so, concluding the definition, we write we have algebras of this operad, and then inside it, we just have some full subcategories, and the category factorization algebra is just a full subcategory. So we have the category of the multiplicative algebras. That's what this M stands for. We have the categories of Weiss algebras. Those are those which, when you restrict them, satisfy this Weiss descent, which I didn't explain yet, but I will explain in a moment. And then if you take their intersection, you get the category of factorization algebras on U. Yeah. And specifically, we also abbreviate because it comes up a lot. So if U is everything, so it's all opens in X, then we just write factorization algebras on X instead of factorization algebras on open X. Okay. So now I need to spend some time explaining what Weiss descent is and how it works and what it does for us. So I think I will need to wipe the board and probably move to this one. Well, I wipe the board. Are there any questions so far? So let's talk about bias descent. Okay, so as I said, this descent, it doesn't care about operads. So for now, just let A just be a functor from this whole set of opens to C. We don't care about the correct structure for now. And then we make the following definition. So let's say we have an open in our collection, and let's say we have a sub-collection of U, which is an open cover of straight U. So i.e., if I take the union of all the things in W, I get exactly U. Then we write so basically we say that we can evaluate A at this cover, and we just define this to be the following. It's just the co-limit over all V that live in only those V that live in U. Everything needs to live in U because that's where A is defined. But we only take those things which live in W down arrow, where, let me say what this is. So this is a notation I will use a lot because it's kind of convenient. This is just a coset of closed opens such that there exists some V in curly V which contains this open. It's like a sieve associated to W. And this expression, we've denoted A of W. And for now, this is what it is. And I will in a moment give you some simpler ways to compute this. So lemma, which is in practice often very useful, which is that if not just W is contained in U, but even the intersection closure of W, so this is the thing you get by taking all things of the form, all possible intersections in W.
What's the definition of
It's those opens for which there exists a W in W that contains O. The existence quantifier refers to the W, but I was a bit lazy and wrote it all in one time. There's just a downward closure of this. You add everything that's smaller than something you already have. And here you do something similar. You just add stuff that's the intersections of something you already have. And if this is still contained in U, and this is the situation which often in practice appears, then one can simplify this formula in two ways. So then A of W can also be computed either by just taking the co-limit of A restricted to this intersection closure of W, or what made this a little bit more familiar, one can compute it as a co-limit of A on the check nerve of W, where this guy here, so this is the co-limit. There are many different ways, so one can write this in a simplicial way. I will instead write it in a cubical way, but they're all very similar. So what this means is you choose some ordering of your W, so this is some ordinal, and you choose some surjection from an ordinal onto W, and then you say, instead of computing the original co-limit, you can just compute the co-limit over finite subsets, finite non-empty subsets of beta and then A evaluated at, so let's call this one, this map alpha, you can take the intersection I in I, alpha I. Okay. So, but note, the point is that in this easy situation where the whole intersection closure is contained in U, then this formula there simplifies significantly. And in particular, if W is equal to its intersection closure, then here it's really just a colimit over W. Okay. So in particular, corollary, if W is intersection closed, then the value is just the column of A on W. Okay. I will come back to this specific the description in a moment. Let's now write the definition. Say it again.
If I want to call it this, is n fixed or not fixed? Is the colimit what's the colimit over the middle colimit?
The middle colimit.
Yeah.
So okay, so W intersection closure. This is a subposet.
It's over.
And
So this the symbol here is a cap, and it's just so this is a sub. Okay, maybe. No. There's no infix. This is a cap. It just means the intersection closure of W, and I just take A, which is defined in all of U, but I can restrict it to this intersection closure and then take the column of it. Okay, yeah, sorry, my handwriting was a bit unrealistic. Okay, I mean, this was just the reason I want. This might be a little pedantic. Maybe I could have skipped this part, but it's surprisingly easy to get confused with exactly what one is allowed to take a colimit over and not. And yeah, so if you take away something from this, is that whenever you read about bias conditions in the literature, you should be really very careful about what exactly one has to take a colimit and how exactly one evaluates, because it's very easy to make mistakes. And yeah, we've also made a fair share of mistakes by trying to work this stuff out.
So the conclusion is A of W can be computed as
just the colimit of A restricted to the intersection closure of W. But this only works if the intersection closure is in U, of course, otherwise it doesn't make sense. And the special case you really should remember, this is really the key one. If this is already intersection closed, then what this is telling you is that you have a super simple formula and you just take the column of W. But I want to warn that this is not true in general. This is really false in general.
so if you want to compute A of W as a colimit of stuff, you better close it.
Yes, exactly. That's exactly right. And this is a very easy mistake to make where one can accidentally write something like this even when W is not intersection closed.
And your definition now.
So the definition is the one I wrote there, but then there's a lemma which are just some relatively straightforward cofinality arguments that we computed in this easier way instead. Yeah. I think I will not go into the proof of this lemma. You can take this as a definition in this case. Yeah. Maybe if necessary, if it's appropriate, I can talk more about these cofinality arguments in the exercise session. Yeah. Yeah, so okay, I should write the definition, which is what does it mean to be a bias sheaf. So we say that A, okay, so there's no bias yet, there's only what does it mean to satisfy the set. We say that A satisfies the set for such a cover and this is just a notation for such a for a cover. So like this is just a shorthand for the thing I wrote there. So W is a collection of opens which jointly cover U. And it satisfies essentially such a cover if the canonical map from A of W to A of U is an equivalence. So this canonical map, you just see like in the terms of those colimits, since W is an open cover of U, everything that appears there are things that are contained in U. So from that colimit canonical maps to A of U, and we want that map to be an equivalence. I will give an example towards the end of this lecture about how it's like one explicit example of such a computation, then you will see. Then you will see what this means. So, note if we require A has descent for all covers, this is going to be the usual sheaf condition. Or I guess since we're doing a covariant functor, this is the usual co-sheaf condition. But this usual co-sheaf condition would not be appropriate in our setting. So let me show you just a very simple example. This is not suitable for us because, for example, if we look at this example I had at the beginning, so this example on X being R, then so we have an open cover where R can of course be covered by taking R without -1 and R without +1. These together form an open cover. And then if I want to evaluate on that open cover, this is not intersection closed, so I better add the intersections. And being an ordinary sheaf would mean that this gets sent to push out. So this would be saying that if you look at, so here I have omega t, here I have to realign with a gap. So I have just 2 copies of the loop space, and then here also, and then here I have 3 copies. And this is not a push out of spaces. So even not homophobic. Okay. So what is the right condition? It's a slightly weaker descent condition where we only have much less covers that we allow. So let's write it. I guess I can probably erase this part. So yeah, now we come to the definition. One more definition. So if I have a cover of some open is called a vice cover. So in an ordinary cover, you would have that every element in U is contained in some open that's contained in W. But now we don't just want that for a single element, but we want that for any finite collection of elements. So for all n and for all finite lists of elements, xn in U, there exists a single W that contains all of them. So of course, jointly the W's to cover them all, but we want that there's one that covers them all. And then we say that our A that is hold this whole time is a Weiss co-sheaf if it satisfies the set for all Weiss covers. Okay. And using these sort of computations that I hinted at before, one can write this condition slightly differently, and I will do so because it is often very convenient. So we have that the following are equivalent. So A is a Weiss co-sheaf. And this is equivalent under the assumption that U is closed under intersection. So U is the same as the closure of U under intersection. In this case, this is the same as saying that for every that we have the co-limit of A on W to U is an equivalence, but now this is not, I can't put an arbitrary covering here because then this would be the wrong expression. So I only do this for all Weiss covers that are intersection closed.
This is A of U though, right?
Yes, thank you. Thank you. Yeah. So in such things, I will just call them Weiss pre-sheaves. And then if U is even downwards closed, so if it contains everything that is smaller than an element that it already contains, then one can write it also like this. It's the same, but now for all Weiss covers such that they are closed downwards, which is what is usually called a Weiss sheaf. So all of these conditions are equivalent as long as the poset U is sufficiently closed. And you will see different versions of this in the literature depending on exactly where you read, but these are all equivalent, and it's basically an immediate corollary of that lemma. That lemma is like not super hard, but one has to do a little bit of finality argument. Okay. And then I want to do one final remark about this definition, and then hopefully we'll have time. Yes, hopefully we'll have time for an example computation. There's one more remark I want to make, because this is another point where unfortunately the literature on factorization algebras can be quite confusing, and so I want to spell this out. Sometimes in the literature, one finds, instead of the Weiss sheaf condition, one finds the so-called Weiss hyper co-sheaf condition. The confusing thing being that often people don't explicitly write it, and that there might be some confusion about which is which. But I just want to spell it out, what the difference is, so that you can recognize it when you see it. And also because it sometimes makes some computation easier. So i.e., so this would be the condition that you have the column of A being U, but now for something more general than what is written here, not just for the W's that are intersection closed or even sheaves, but for all hyper covers W, for all Weiss hyper covers W of U. And what does this mean? i.e., so first of all, we have an ordinary Weiss cover. But then instead of asking that it is intersection closed, you ask that whenever you take some W that lives in the intersection closure of it, so this might not itself be W because you don't ask for this to be intersection closed. The only thing you ask is that if you take only those W that live under this fixed W, you want that this is again a vice. This is sort of a weaker condition where if this W is already here, then this would just be like the general cover. So this would be pathological. But yeah, so you have this weaker, it's a stronger condition because instead of just asking it for the ones that are close on the intersection, you ask it for this more general version of covers.
Sorry, the down arrow should be the 30.
No. So what this means is I take all the things in curly W that live under this fixed W, this straight W. Okay. Yeah, this condition is not super important, but I just wanted to mention it because it can be very confusing. Yeah.
And it's also equivalent.
No, this is not equivalent. That's somehow the. Sorry, maybe I should. Sorry, maybe. This is. Or. Okay, let me be precise. I actually don't know if it's. Like, maybe there are special cases where it is equivalent, but at least it's not like formally equivalent. Like, maybe there might be some good spaces on which it is equivalent. So this is not. Yeah. That's why I really want to make this remark because they're really different, but like very subtly so, and it's easy to get confused between the two. Okay, so I have 10 or a little bit less than 10 minutes. So let me show you what one can do with this vice condition, because maybe now it seems a bit like kind of unmotivated. So let me explain, let me do a sample computation. And then you will see at least maybe somewhat why this is a reasonable condition. So, so there is a factor. So okay, let's say that let A, B, and C be associative algebras. I'm going to be a little bit vague. You can take them to be strict algebras if you want, or some U1 algebras if you like. And let's say we also have some bimodules, pointed bimodules. So let's say we have a AB bimodule M and a BC bimodule N. Then there is a factorization algebra on R. And I will just tell you what this factorization algebra does on intervals. So I'm going to mark two special points on my real line. I'm going to mark -1 and +1. And I'm going to tell you what this factorization algebra does on intervals. I won't tell you what it does on more general things for now, and we will then do a non-trivial computation. So so there are a couple of different types of intervals that exist on the real lines. There are the ones that are fully contained in this left part, and those are going to be sent to A. And then the ones that are fully contained in this middle part are going to be sent to B, and the ones here are going to be sent to C. And so that if you forget about everything here, you see that this is a little bit like the very first example, where if you have two copies of C, they will embed into a bigger copy of C, and that's where you use the algebra structure here. So this is using the algebra structure, the associative algebra structure. But then we also have these special points, +1 and -1, and we say that every open that contains one of them gets sent to the two modules. And then you will see that using the module structure, using the bimodule structure, you get this. And so for example, if you have this bigger open, that still contains this point, so it still gets sent to N. And then the structure map that goes from this tensor this to this one is just the multiplication map of the algebra. And then similarly, the fact that you can make this even bigger to contain both a B and a C means that the two actions are compatible. So this is really a bimodule structure. So here this blue thing is using bimodal structure. Okay, and now there's conspicuously missing one interval type that I didn't tell you what its value is, but I claim we can compute it from the Weiss condition.
Maybe it fell down.
Yeah, thank you. Okay, so the question is, what is, so let's call this factorization algebra A. So the question is, what is A evaluated at the whole real line? Because you see the whole real line contains both this point and this point. It's not one of any of the types that I told you about. And so we have to compute this. And I claim that this one can do using the Weiss condition. And so that way you can see it in action. Yes, thank you very much. So consider W to be the subposet of opens of R, which is given by things of the form where you take R minus K, where K is in curly K, and what is curly K? So curly K is the set of compact subsets of minus 1, 1 with finitely many, compact non-empty subset of minus 1, 1 with finitely many connected components. And then we take all complements of such things. So basically, pictorially, we have this, and then we sort of remove finitely many intervals, but only between 1 and minus 1. We never remove anything on the outside. And now, if you look at this closely, you will see that W is a Weiss cover. Because if you have finitely many points, you can just choose your compacts so that they miss all the finitely many points. And so then if you remove the compacts, those finitely many points will be in the open. But in fact, it is even intersection closed, which means that we're in a good case where we just have to compute a colimit. And now I claim that we can compute this colimit. So there's a fact that one needs for this, which maybe some of you have seen, which is that, so K, of course, has a map to here, which is an isomorphism, which just takes K to its complement. But there's a fact that is that there's a map from K to delta that just sends K to its set of connected components, which is linearly ordered. Therefore, it's an element n that is finite and linearly ordered and non-empty, so it's a well-defined element in here. And there's a fact, which is that this is in fact a localization map. Yeah, this is not like super trivial fact, but I will just accept it for now. One can show that this is a localization map. And using this, we can now compute, because we have W goes to C, and we're supposed to compute the colimit of this. But of course, W is just K op, and K op localizes to delta op, because K localizes to delta. And if it's a localization map at what? Well, at the pi0 isomorphisms. And this map A, if you look at what it does on pi0 isomorphisms, it will just be an equivalence or the identity, because pi0 isomorphism means you cut out the same number of compacts in the middle, and so you will just get a copy of A, you will just get a copy of M, then a bunch of copies of B, and then a copy of N. So by the way the A is defined, this will factor uniquely to this localization. And in fact, since it's a localization, this is cofinal. And so we can compute the co-limit of A on W by just computing the co-limit of this thing that I will maybe call A prime on delta up. And if you explicitly look at what this really is, one can write it like if I have n in delta up, then what do I have to do? I have to remove n plus 1 many small intervals from here. So if I go labeled 1 up to n, and then the thing that remains, what is the thing that remains? Well, here I have a copy of m because it contains this special point. Here I have a copy of n because it contains this special point. And all these intermediate ones, it's going to be a copy of b. And so it's going to be the co-limit of n in n over this expression here. And this is really just what one usually would call the tensor product of m and n. Okay, I think I am out of time, so I will stop here and thank you for your attention.
Any questions?
Yes.
You have this example which is closely related behind on the
Yes.
Not a cover of the subtype.
Exactly. This is yes. Okay, thank you. So the question is, why is it not a vice cover? Well, so how the cover, the way it looks is I have covered my R by this guy where I have a hole here, and this guy where I have a hole here. And now if I take the set of exactly these two elements, that will be a finite set. So, but it's not contained either here nor here. So this is not a well-defined vice cover. I don't know if this was the question of. Yes, exactly. Thank you for the question. Yes?
Why do you need 5 modules here?
Yeah, this is a bit of an annoying thing about this story, which is that there's always the empty set that exists, and the empty set will be sent will be just sent to the monoidal unit, and then the inclusion of the empty set into B will just be the unit of the algebra, but then I will also have an inclusion of the empty set into opens of this type, and that will give me a pointing of this module. Maybe I should mention that to answer this question also, so I won't really talk about this in this course, but there is also a pointless version of factorization algebras. So this is in the PhD thesis of Armin Carlson, where basically the definition is adapted in such a way to exactly avoid this, because often in practice one doesn't want to have quantified modules, and one can avoid this by tweaking everything a little bit, but I won't go into more detail in this course.